Hello class, this is section 2.5, non-homogeneous equations and undetermined coefficients. So for the non-homogeneous equations, the general non-homogeneous nth order linear equation with constant coefficients has the form a sub n times the nth derivative of y plus a sub n minus 1 times the n minus 1th derivative of y, adding it all the way down until we get to a sub 1 times y prime plus a sub 0 times y is equal to some function f of x. By Theorem 5 of section 2.2, from what we have previously discussed, the general solution has the form y is equal to y sub c plus y sub p, where the complementary function y sub c of x is a general solution of the associated homogeneous equation a sub n times the nth derivative of y plus a sub n minus 1 times the n minus 1th derivative of y, all the way down to a sub 1 times y prime plus a sub 0 times y is equal to 0, and y sub p is some particular solution. So let's say, for example, we want to find a particular solution of y double prime plus 3y prime plus 4y is equal to 3x plus 2. We are going to let f of x be 3x plus 2. And, this is linear. And since that's linear, it has a degree of 1. So because of that, we could have our initial guess for the particular solution to be y sub p of x is equal to ax plus b, since that's also linear, a polynomial of degree 1. From this, we know the first derivative of y sub p is just a, and the second derivative of y sub p is, 0. So because of that, we know that y sub p will satisfy the differential equation if, and let me give myself some more space to write this, 0 plus 3 times a plus 4 times ax plus b is equal to distributing and collecting like terms. We have 4 times ax plus 3a plus 4b. And that has to be equal to 3x plus 2, our function, for all values of x. So when does that happen? Well, we could equate the coefficients. This 4a has to be equal to 3, which means that a is going to be 3/4. Likewise, 3a plus 4b has to be equal to 2. And so we could solve for b and get ourselves a value of negative 1/16. So our particular solution is going to be y sub p of x is 3/4 times x minus 1/16. For example number 2, I want to find a particular solution of y double prime minus 4y is equal to 2 times e to the 3x. So we know that any derivative of e to the 3x is a constant multiple of e to the 3x. Right, first derivative would just be 3e to the 3x. Second would be 9e to the 3x. So because of that, we are going to try as our particular solution y sub p of x is equal to a times e to the 3x. So because of that, first derivative of y sub p would be 3a times e to the 3x. And the second derivative of y sub p is 9a e to the 3x. So we know that this would be satisfied, our differential equation, if 9a times e to the 3x minus 4a times e to the 3x is equal to 2 times e to the 3x. So combining like terms, our coefficients have to satisfy 5a is equal to 2, which means a is 2/5. So our particular solution is going to be y sub p of x is equal to 2/5 times e to the 3x for this particular differential equation. Example 3, we want to find a particular solution of 3y double prime plus y prime minus 2y is equal to 2 times the cosine of x. So for this one, we are going to try the following solution for y sub p of x, being a times the cosine of x plus b times the sine of x. So when we take the first derivative of y sub p, we will get negative a times the sine of x plus b times the cosine of x. And when we take the second derivative of y sub p, we get negative a times the cosine of x minus b times the sine of x. And let me make my sign here a bit more legible. There we go. So, equating everything in the differential equation and writing everything out, this will be 3 times negative a times the cosine of x minus b times the sine of x plus negative a times the sine of x plus b times the cosine of x minus 2 times a times the cosine of x plus b times the sine of x. And that's supposed to be equal to 2 times the cosine of x. So we could also now equate all of these terms nicely, right? So combining like terms, which we do indeed have a bit of, right? Negative 3a minus 2a, so this be negative 5a plus just this b here is going to be equal to our only coefficient on the right-hand side, 2. And then for the sine terms, this would be negative a minus, we have negative 3b, negative 2b, so negative 5b. And that'll be equal to 0 because there's no sine term on the right-hand side. So solving this system of equations, we get A being -5/13 and B being 1/13. So our particular solution is going to be y sub p of x. And that's presuming my handwriting is legible for that. Y sub p of x is equal to -5/13 times the cosine of x plus 1/13 times the sine of x for this particular differential equation. For example 4, I want to find the particular solution of y double prime minus 4y is equal to 2 times e to the 2x. So we could try, right? Y sub p of x is a times e to the 2x, just like we did one of those previous examples before, right? So based on our differential equation, right, we would have, the second derivative of y sub p to be 4a e to the 2x. So we could put that in, substitute and all that, to give us 4 times a times e to the 2x minus 4a e to the 2x. But we have a problem. These terms cancel out. And that, of course, cannot be the value of 2 times e to the 2x, because the exponential function never equals 0. So can't use that as our solution, unfortunately. So let me separate this. So because of that, we cannot use that, right? But we could try something a little different. Let's try y sub p of x, right? Since we know that, we need that e to the 2x in there. But why don't we multiply that by an x? A times x times e to the 2x, right? Well, let us see what we get for this. Y sub p, the first derivative of y sub p, this will be a times e to the 2x plus 2a x e to the 2x. And the second derivative of y sub p, this would be 4a e to the 2x plus 4a x e to the 2x. And as I quickly fix that 4. Right, due to the product rule for differentiation. So now we could plug in our parts into our differential equation up here. This would be 4a e to the 2x plus 4a x e to the 2x minus 4a x e to the 2x. And this would be equal to 2e to the 2x. Right, so we do still have that cancellation of terms, right? This term and this term. But now we don't have just nothing on the left-hand side. This does nicely give us 4a e to the 2x is equal to 2e to the 2x. And well, that's solvable, right? A here would just be a half. So our particular solution this would be y sub p of x is equal to a half times x times e to the 2x. So this gives us our method of undetermined coefficients. So this is straightforward when the ordinary differential equation is sufficiently simple. where we can make an intelligent guess as to the general form of the particular solution, which is basically what we were just doing. This applies whenever the function f of x from our ordinary differential equation is a linear combination of finite products of functions of some polynomial in x, an exponential function e to the rx, something involving cosine of kx or sine of kx. As we saw, those are pretty nice enough to solve. But, of course, not every equation is simple. And we have a couple of rules to address that. Rule 1 for this. Suppose that no term appearing either in f of x or in any of its derivatives satisfies the associated homogeneous equation L times y is equal to 0. Now we take as a trial solution for y sub p a linear combination of all linearly independent such terms and their derivatives. Then determine the coefficients by substituting the trial solution in the non-homogeneous equation L times y is equal to f of x. In practice, we want to check the supposition by using the characteristic equation to find the complementary function, and then write a list of all the terms appearing in f of x and its successive derivatives. If none of the terms in the list duplicates a term in y sub c, so that complementary solution, then we proceed. So what does that mean? Well, example 5, we're going to find a particular solution of y double prime plus 4y is equal to 3x cubed. So for this, we need to know our complementary function, always the general idea of it. So a complementary function, y sub c of x, would take the form of something involving c sub 1 times the cosine of 2x plus c sub 2 times the sine of 2x. Why is that? That's because based on the homogeneous equation here, right, we would have a characteristic equation of r squared plus r, 4 times r is equal to 0, which, we could factor. R times r plus 4 is equal to 0. And we would get values here to then be based on the following values. R is 0, r is negative 4. Which would then allow us then to substitute inside of there for us to get our different values. But we don't need to worry about those particular ones per se. Oh, excuse me, I just noticed something. There's no r here. Characteristic equation for this, because that's y double prime plus 4y, which will be the associated homogeneous equation, is equal to 0. Characteristic equation, r squared plus 4 is equal to 0. R here would be positive and negative 2i, which would give us our complex solutions and be of this form for the complementary function. But here we have f of x being 3x cubed, right? The derivatives of f of x are linearly independent functions. And these include, well, the original x cubed, x squared, x, and 1. And, none of these are in y sub c. So we could proceed. Y sub p of x. An initial guess of that would be some linear combination of those. A times x cubed plus b times x squared plus c times x plus d. So now we can take the derivative. First derivative of y sub p. 3ax squared plus 2bx plus c. The second derivative of y sub p would be 6ax plus 2b. So we could plug those now into our differential equation. This is going to be 6ax plus 2b plus 4 times ax cubed plus bx squared plus cx plus d. And we can, combine some terms and make it a little tiny bit nicer to help us with our equality in a moment. This would be 4ax cubed plus 4bx squared plus 6a plus 4c times x plus 2b plus d is equal to 3x cubed. So we have a whole bunch of equations we could solve, right? 4a is equal to 3 based on our only coefficient over here. Then the other ones, 4b is 0, 6a plus 4c is 0, and 2b plus d is 0. So from the system of equations, we get the following solutions. A is 3/4. B and D are both 0. And C is -9/8. So that does help us simplify our particular solution a bit. To B, y sub p of x is 3/4 times x to the third power minus 9/8, 9/8, excuse me, times x. For example 6, I want to solve the initial value problem, y double prime minus 3y prime plus 2y is equal to 3e to the negative x minus 10 times the cosine of 3x, with y of 0 being 1, y prime of 0 being 2. So for the complementary function, we need to solve our characteristic equation. This being r squared minus 3r plus 2 is equal to 0. And this factors nicely to give us solutions, r sub 1 being 1 and r sub 2 being 2. So a complementary function would be y sub c of x is c sub 1 times e to the x plus c sub 2 times e to the 2x. And we know f of x here is 3e to the negative x minus 10 times the cosine of 3x. So its derivatives include e to the negative x, cosine of 3x, sine of 3x. And thankfully, none of these appear in the complementary function. So we could try for a particular solution. A times e to the negative x plus b times the cosine of 3x plus c times the sine of 3x. So because of this, y sub p prime is negative a times e to the negative x minus 3b times the sine of 3x plus 3c times the cosine of 3x. The second derivative of y sub p would be a e to the negative x minus 9b to the cosine of 3x minus 9c times the sine of 3x. And finally, the third derivative of y sub p. This will be oh, excuse me, we do not need the third derivative. We just need to go up to the second. So to plug it into our differential equation, this is going to be, and of course, combining different terms and whatnot to make this a bit easier to read. Plugging it in gives us 6a e to the negative x plus negative 7b minus 9c times the cosine of 3x plus 9b minus 7c times the sine of 3x. And this would be equal to 3 times e to the negative x minus 10 times the cosine of 3x. So after doing that, we could solve to get our various system of equations. This would be 6a is equal to 3, negative 7b minus 9c is equal to negative 10, 9b minus 7c is equal to 0. From this system of equations, we get a is a half, b is 7/13, and c is 9/13. So our particular solution for this is y sub p of x is equal to a half times e to the negative x plus 7/13 times the cosine of 3x plus 9/13 times the sine of 3x. Which is all nice and dandy and whatnot. But if we put in a 0 into here, we get a half. We get a half plus 7/13. And that does not work, right? We don't get a value of 1. Since we get, what is that, 6.5 plus 7, and that does not make the 1. So this does not satisfy it. So this cannot be a particular solution involving this. So we put a red X here to denote that fact, unfortunately. So what does that mean? Well, we could look at the general solution. Because we just followed exactly what we already know. This would be y of x, which is supposed to be y sub c of x, plus y sub p of x. So in terms of this would be c sub 1 times e to the x, plus c sub 2 times e to the 2x, plus a half times e to the negative x, plus 7/13 times the cosine of 3x, plus 9/13 times the sine of 3x. Right? And if we were to take the derivative here, if we were to take the derivative, y prime of x, we would get c sub 1 times e to the x plus 2 times c sub 2 times e to the 2x minus a half times e to the negative x minus 21/13 times the sine of 3x plus 27/13 times the cosine of 3x. So now, because of this, the initial conditions that we have will give us y of 0 is equal to c sub 1 plus c sub 2 plus a half plus 7/13 is supposed to be 1, and y prime of 0 is c sub 1 plus 2 times c sub 2 minus a half plus 27/13 is supposed to be equal to 2. So I'll write this last little bit up here, just so I don't have to erase everything down below. The solutions we get for that, we get c sub 1 would be negative a half, and c sub 2 is 6/13. So despite that particular solution not completely working in our initial conditions, we were able to use the general solution for it. And this will give us our particular solution now involving this initial value problem. To be y of x is negative a half times e to the x plus 6/13 times e to the 2x plus a half times e to the negative x plus 7/13 times the cosine of 3x plus 9/13 times the sine of 3x as our complete solution involving that. One more tame version. We're going to find the general form of a particular solution of the third derivative of y plus 9 times y prime is equal to x times the sine of x plus x squared times e to the 2x. Characteristic equation for the associated homogeneous differential equation will be characteristic equation. And this will be r cubed plus 9r is equal to 0. So the roots that we would get are 0 and positive and negative 3i. So the complementary function. Complementary function. This will be y sub c of x is equal to c sub 1 plus 2, c sub 2 times the cosine of 3x plus c sub 3 times the sine of 3x. So the derivatives here involve well, let's see. Cosine of x, sine of x times the cosine of x times the sine of x. All of these ones here involving our original f of x up here. And then additionally, we would also have e to the 2x from here, x times e to the 2x from these two, x squared times e to the 2x also from here. So there's none of these appear in the complementary function. As we could see, none of those terms are in here. So our particular solution, very nice, is going to be a times the cosine of x plus b times the sine of x plus c times x times the cosine of x plus d times x times the sine of x plus e times e to the 2x plus f times x times e to the 2x plus g times x squared times e to the 2x. So now the second rule for that method of undetermined coefficients, if the function f of x is of the form p sub m of x times e to the lx times the cosine of k times x, or p sub m of x times e to the lx times the sine of kx, with p sub m of x as a polynomial in x of degree m. We take as our trial solution y sub p of x is equal to x to the s power times a sub 0 plus a sub 1 times x plus a sub 2 times x squared, all the way down to a sub m times x to the m times e to the lx times the cosine of kx plus b sub 0 plus b sub 1 times x plus b sub 2 times x squared, all the way down to b sub m times x to the m times e to the lx times the sine of kx, where s is the smallest non-negative integer such that no term in y sub p duplicates a term in the complementary function y sub c. Then we would determine the coefficients by substituting y sub p into the non-homogeneous equation. In practice, though, we have a few common cases or functions that are the sum of common cases. F of x is equal to f sub 1 of x plus f sub 2 of x. So we could take y sub p as the sum of trial solutions, choosing s separately for each part to eliminate duplication with that complementary function. So those include these in the table below. So if our function includes p sub m is b sub 0 plus b sub 1 times x plus b sub 2 times x squared, all the way down to b sub m times x to the m. This would be x to the s times a sub 0 plus a sub 1 times x plus a sub 2 times x squared, all the way down to a sub m times x to the m. If the function is a times the cosine of kx plus b times the sine of kx, y sub p would be x to the s times a times the cosine of kx plus b times the sine of kx. If the function is e to the lx, that would be a times the cosine of kx plus b times the sine of kx. The particular solution would include x to the s times e to the rx times a times the cosine of kx plus b times the sine of kx. If the function includes p sub m of x times e to the r, p sub m of x times e to the r times x power, the particular solution would include x to the s times a sub 0 plus a sub 1 times x plus a sub 2 times x squared, all the way down to a sub m times x to the m times e to the rx. And then finally, p sub m of x times a times the cosine of kx plus b times the sine of kx. That would include this lovely long thing. X to the s times a sub 0 plus a sub 1 times x, all the way down to a sub m times x to the m times the cosine of kx plus b sub 0 plus b sub 1 times x, all the way down to b sub m times x to the m times the sine of kx. So let's say, for example, I have example 8. This being, we want to find a particular solution of the third derivative of y plus the second derivative of y is equal to 3e to the x plus 4x squared. Characteristic equation. Let me write that up here to make sure I have enough room. Characteristic equation is going to be r cubed plus r squared. This will be 0. So the roots we get are r sub 1 and r sub 2, both being 0, and r sub 3 being negative 1. So, complementary function. Complementary function. This would be y sub c of x is c sub 1 plus c sub 2 times x plus c sub 3 times e to the negative x. So, because of that, our trial solution can be a times e to the x plus b plus cx plus dx squared, right? And we know that a e to the x is equal to 3e to the x. This does not duplicate the complementary function. However, though, for the b plus cx plus dx squared, that is unfortunately a part of it instead of our complementary function, at least of the first two terms. So if we just multiply by an x, we still have duplication. So we need to multiply b plus cx plus dx squared by x squared. And that will help us to eliminate the duplication. So y sub p is going to be a e to the x plus bx squared plus cx cubed plus dx to the fourth. So first derivative of y sub p would be a e to the x plus 2bx plus 3cx squared plus 4dx cubed. Second derivative of y sub p, a e to the x plus 2b plus 6cx plus 12dx squared. Third derivative of y sub P A e to the x plus 6c plus 24dx. And we could plug that into our differential equation now. So this is going to be 2a times e to the x, and combining these terms and whatnot, this would be plus 2b plus 6c plus 6c plus 24d times x plus 12d. Let me write that a little bit more legible. Plus 12dx squared. This is equal to 3e to the x plus 4x squared. So equating coefficients, we get 2a is equal to 3, 2b plus 6c is 0, 6c plus 24d is 0, 12d is 4. This solves to give us a is 3/2. B is 4. C is -4/3. D is 1/3. So our particular solution would then be the following. Y sub p of x is 3/2 times e to the x plus 4x squared minus 4/3 times x cubed plus 1/3 times x to the 4th. Example 9, we want to determine the appropriate form for a particular solution of y double prime plus 6x, y double prime plus 6y prime plus 13y is equal to e to the -3x times the cosine of 2x. The characteristic equation takes the form of r squared plus 6r plus 13 is 0. And this gives us solutions of -3 plus or minus 2i. So complementary function would be y sub c of x is equal to e to the -3x times c sub 1 times the cosine of 2x plus c sub 2 times the sine of 2x. But we could kind of see this already going on, right? We have some duplication here involving these two. So to avoid duplication, we want to multiply by x. So y sub p of x is going to be e to the -3x times ax times the cosine of 2x plus b times x times the sine of 2x. For example 10, I want to determine the appropriate form for a particular solution of the 5th order equation d minus 2 cubed times d squared plus 9 times y is equal to x squared times e to the 2x plus x times the sine of 3x. So, characteristic equation. Would be r minus 2 cubed times r squared plus 9 is equal to 0. This will give us solutions of 2, 2, 2, so 3 2's, and a positive and negative 3i as our 5 solutions. So complementary function would be the following. Y sub c of x is c sub 1 times e to the 2x plus c sub 2 times x times e to the 2x plus c sub 3 times x squared times e to the 2x plus c sub 4 times the cosine of 3x plus c sub 5 times the sine of 3x. So we want to try for the particular solution the following. So this is going to be a plus bx plus cx squared, the whole thing multiplied by e to the 2x, plus d plus e times x times the cosine of 3x plus f plus g times x times the sine of 3x. And I should probably be consistent with my bracket. Okay. So in order for us to get this solution, we need to multiply. I will write it this way. This left-hand side right here by x cubed. Why is that? That's because of, instead of here we go all the way up to x squared, which is what this went up to. So to avoid all the duplication, it needs to be x cubed. And this right-hand side, also to avoid the duplication, this will just be by x, involving these last two terms. So the particular solution that we are going to get which will be sadly very long, y sub p of x is a x cubed plus b x to the 4th plus c x to the 5th times e to the 2x plus dx plus ex squared times the cosine of 3x plus f times x plus g times x squared times the sine of 3x. So now this variation of parameters, presuming the integrals that appear can be evaluated, this method can always be used to find a particular solution of the non-homogeneous linear ordinary differential equation. And that would be the nth derivative of y plus p sub n minus 1 of x times the n minus 1th derivative of y, all the way down to p sub 1 of x times the first derivative of y plus p sub 0 of x times y is equal to f of x, provided that we already know the general solution, y sub c is equal to c sub 1 times y sub 1 plus c sub 2 times y sub 2, all the way down to c sub n times y sub n of the associated homogeneous equation, nth derivative of y plus p sub n minus 1 of x times the n minus 1th derivative of y, all the way down to p sub 1 of x times y prime plus p sub 0 of x times y is equal to 0. So, theorem 1, variation of parameters. If the non-homogeneous equation y double prime plus p of x times y prime plus q of x times y is equal to f of x has complementary function y sub c of x is equal to c sub 1 times y sub 1 of x plus c sub 2 times y sub 2 of x, then a particular solution is given by this. Y sub p of x is equal to negative y sub 1 of x times the integral of y sub 2 of x times f of x divided by w of x dx plus y sub 2 of x times the integral of y sub 1 of x times f of x divided by w of x dx. W of x is w of y sub 1 comma y sub 2. It is the Wronskian of the two independent solutions y sub 1 and y sub 2 of the associated homogeneous equation. So, example 11. We want to find a particular solution of the equation y double prime plus y is equal to tangent of x. So, a complementary function. And let me write that up here so I have enough room for the remainder. Complementary function y sub c of x is c sub 1 times the cosine of x plus c sub 2 times the sine of x based upon our characteristic equation being r squared, specifically being equal to, r squared plus 1 is equal to 0. So because of that, we would get, let me actually write that. This is from the characteristic equation. R squared plus 1 is equal to 0. So r is positive and negative I, as we could see in our equation. So for this, we are going to let y sub 1 be the cosine of x. Which means the first derivative of y sub 1 is the negative sine of x. Likewise, y sub 2 is going to be the sine of x. So y sub 2 prime is going to be the cosine of x. So the associated homogeneous equation will be some derivative u sub 1 prime times the cosine of x plus some derivative u sub 2 prime times the sine of x is supposed to be 0. And putting it into our differential equation, we would obtain u sub 1 prime times the negative sine of x plus u sub 2 prime times the cosine of x is equal to the tangent of x. So we could solve this. We get u sub 1 prime is equal to negative sine of x times the tangent of x. And that is equal to negative sine squared of x over cosine of x. But from trigonometry, this is just the cosine of x minus the secant of x. And u sub 2 prime would be cosine of x times the tangent of x. And this just nicely becomes the sine of x. So, to obtain the original functions, u sub 1, this will be the integral of the cosine of x minus the secant of x dx. This is sine of x minus natural log of the absolute value of the secant of x plus the tangent of x. And u sub 2 will just be the integral of the sine of x dx, that being negative cosine of x. So our particular solution is going to be y sub p of x is u sub 1 of x times y sub 1 of x plus u sub 2 of x times y sub 2 of x. In our case, this will be the sine of x minus the natural log of the absolute value of the secant of x plus the tangent of x times the cosine of x plus negative cosine of x times the sine of x. And this nicely simplifies to negative cosine of x times the natural log of the absolute value of the secant of x plus the tangent of x. Let me know if you have any questions or concerns. Thank you.